Okay, friends, welcome back. And just before the break, we solved a problem, very simple problem, but there were two lessons that we learned from there. The first one, or rather the second one, is that under natural convection circumstances, we must not ignore the contribution of radiation. That can be significant and in many cases be even more than the amount of heat transfer or heat exchange that you can accomplish by natural convection alone. So mostly it will be natural convection plus radiation. Okay, sometimes we think that, oh, natural radiation effects only become important when the temperature differences are very high. That is not the case. That may be for forced convection, but for natural convection, um, I mean, the heat exchange may not be high, but it is quite comparable to what you will get by natural convection. So many a times what we say is, if you have to estimate, and they say, okay, if I keep a hot cup of tea in a room to cool down, what will be the effective heat transfer coefficient? And well, while natural convection will give you probably around 5, 6, something like that. We say, okay, no, we can consider it to be 10, uh, and which is going to be a combined heat transfer coefficient, taking into account the effects of both convection and radiation. Okay, let me start sharing again, and we'll go back and forth in the slides and the notes, handwritten notes. Okay, so let's come back to the slides again. So all this while we were talking about forced convection, sorry, vertical plates, right? So let us now look into what happens if the plates are not vertical and instead they're horizontal. Okay. Now, if the plate is horizontal, then the next question is, okay, if this is my plate, is the hot side facing up or is the hot side facing down? See, if the hot side is facing up, then what happens? The flow comes in, gets in touch, it comes in contact with the hot surface, becomes hot, becomes light, and moves up, because that's the natural tendency. Okay. But on the other hand, if it is facing down, it becomes a problem, because the air that comes in contact with the hot surface becomes hotter. Its tendency is going to rise. Its tendency will be to rise, but it cannot because it is obstructed by the plate. So it will have to come on the side and then make its way up from there. Okay. So therefore, for horizontal surface, it is very important to note what is the orientation. Right? Forced convection, it doesn't matter whether the flow is at the top or the bottom, because that is it's flow. But here it's gravity assisted flow, so the direction is important. So for a hot surface facing up or a cold surface facing down, which are equivalent conditions, we have correlations for Nusselt number, which is quite similar. Sorry, I mean, which is quite simple. What you see is 0.5, Nusselt is 0.54 Rayleigh to the power 1/4 when the Rayleigh number is between 10 to the power 4 and 10 to the power 7, and then 0.15 Rayleigh to the power 1/3 when it is above 10 to the power 7. Again, remember here that the transition to turbulence happens at a lower value of Rayleigh number compared to vertical plate. Vertical plate was 10 to the power 9. Here it's 10 to the power 7. Okay. As before, the dependence on Rayleigh or Grashof is 1/4 in laminar and 1/3 in turbulence. Okay, I've just put a small question at the bottom. How does the effect, if Nusselt, average Nusselt number varies at Rayleigh L to the power 1/3, how does the average heat transfer coefficient depend on L? Okay, you can work it out. Nusselt, average Nusselt is H bar times L by K. So you have an L on the right hand side, on the left hand side. And on the right hand side, again, you have Rayleigh to the power 1/3. Rayleigh has an L cubed inside. So which means that the exponent of L on the right hand side is again 1. So therefore, what it means is that the average heat transfer coefficient does not, for turbulent flow, or when the dependence is relative to the power 1/3, the average heat transfer coefficient is independent of the length of the plate. Okay. So again, correlation based, you have these correlations at your disposal. You have to look at the situation, figure out which correlation to use. This condition, very difficult because my hot fluid wants to rise, but it cannot. Wherever it is coming, it cannot. It has to go to the edge and then make its way along the outer edges of the plate. Its tendency is going to rise, but the plate itself is obstructing it. So look at this, Nusselt number is 0.27 relative to the power half. There will be some flow, okay, some heat transfer. And this is in this whole range of 10 to the power 5 to 10 to the power 10. Okay. So these are again all empirical correlations, and that's why you have this range of Rayleigh numbers, because this is the number range in which the experiments were conducted. Maybe below 10 to the power 5, you did not get any appreciable heat transfer. Okay. So whether it's a hot plate facing down or the cold plate facing up, it's the same situation. The cold plate, the cold air's tendency is to sink, is to come down, but it cannot because the plate is coming in the way. So it has to go around the plate and then come down. Okay. All right. So let's again move back here and quickly write down what we just discussed. Sorry. Okay, something is horizontal plates. Refer to slides. Okay. But what we saw is that if it's a hot plate facing up, hot side facing up, you have higher heat transfer. If it's facing down, there's a problem because the fluid cannot make its way around the fluid has to make its way around the plate. Now, the question is what happens if the plate is inclined? Okay. So in other words, plate is like this. This is G. Okay. This is theta. Same thing for a cold plate as well. And if I try to draw it, oops. Okay. This is when TW is greater than T infinity. This is when TW is less than T infinity. Let me write it a little. Now, what is happening here? The buoyancy force will now have two components, one parallel to the plate and one normal to the plate. Right? So let's write it down. F buoyancy has two components. Parallel to the plate and normal to the plate. Okay. Now, what is the effect on this of this? Okay. So let's consider this one. The first thing is H for H bar reduces on the bottom side due to reduction of gravitational component. Okay. And what we do is for theta from 0 to 60 degrees, we can use the vertical plate correlation by substituting G by G cos theta. Okay. So in Rayleigh number or Grashof number, that G has to be replaced by G cos theta. Okay. So let me, if I try to draw this, now you have to visualize. Okay. The hot plate, the tendency of the fluid will be to move up, but the plate is not allowing it to move up. So therefore, this boundary layer is going to form on this surface. That is the bottom surface. Okay. Likewise, for the cold plate, on the top surface, this boundary layer is going to form. It wants to sink, but the plate will not let it go. So let me use this color so that we don't get confused. Let's use the black color only. However, from the top surface, what happens is, as the fluid rises, its tendency is to go vertically up, isn't it? So while the viscous forces is going to pull it back and let it cling to the surface, its tendency will be, there will be a tendency to detach. So what happens is, there are packets of hot air that detaches from the surface and leaves. Similarly here also, there are packets of cold air whose tendency would be to detach from the surface. Okay, so therefore I'm writing it for let us say, yeah, for TW greater than T infinity. I'm writing it top and bottom like that, but it's exactly the same logic for the cold plate as well. Okay, so on the top side, there is release of pockets of hot fluid, sorry, packets of hot fluid, sorry, disturbing the boundary layer formation. So what is the net effect? H increases, but however, there are no standard correlations. Okay, so once again, look into this. At the bottom surface on the left hand plot, that is, the air wants to rise, but the plate obstructs it. It has to go, it has to cling to the plate, reach the top edge, and then escape. Top surface, however, the hot, even if it is inclined, the air would like to move vertically up, not along the plate. The plate would like to, because of viscous forces, would like to pull it down. But at some point, if the buoyant forces are strong enough, packets of this hot fluid will detach from the surface and move up. And as it moves up, the net effect is going to be increase in overall heat transfer rate. And therefore, H bar, which is the average heat transfer coefficient, increases. Okay. All right. Let's now move back again to the slides. Okay. I have put in these inclined plates, refer to class notes, so you won't have a problem. Okay. Now, so far for hot flat plates, okay, flat plate, horizontal, flat plate, vertical, blah, blah, blah. Okay. Now let us try to find out what happens if for other geometries, external flows. So what happens if it's a hot cylinder? Very common. Hot tubes. We have seen, for example, flow over a bundle of cylinders or a single cylinder or a sphere. So instead of flow, if the heat transfer requirement or the heat generation is not high enough, it can be cooled by natural convection as well. Okay. So if that is the case, what happens? So if you consider a long horizontal cylinder, what happens? The air will try to use the pen here. The air first comes in contact with the hot surface and it gets heated, it gets lighter, it would try to rise. How will it rise? Of course, the cylinder itself will inhibit its movement. So it is going to go cling to the cylinder surface and move up. And as it moves up, the boundary layer thickness keeps increasing or keeps growing. And if the boundary layer thickness increases, my heat transfer coefficient and therefore my Nusselt number, local Nusselt number will come down. Okay. Anyway, so it goes up and finally when it reaches the top, okay, it gets released in the form of a plume, what is called a plume, this term. Okay, so you have this plume of hot air that rises up, that flows around the surface, gains momentum, and then rises up from the top. So if I now look at the Nusselt number variation, what will happen? When the boundary layer thickness is the lowest, is the thinnest, the heat transfer is highest, so Nusselt number is highest. And then as you go from theta equal to 0 and you increase to theta equal to pi by 2 and then to pi, and local Nusselt number will go down. Okay. So you understand? Any questions? Understanding the physical significance? So what happens is there's this packet of hot air. If you now somehow put your hand inside this plume, you'll be able to feel the hot air. Okay. And there is this average Nusselt number correlation for this, which is whatever 0.387 blah blah blah. Okay. Sorry, not 0.387, 0.60 plus 0.387 relative to the power 1/6, etc. This is also Churchill and Chu's correlation. So this, unlike forced convection where there is flow separation and eddies created, the plume actually rises. Yeah, eventually as it rises, it is going to disperse. It is going to, due to flow instability, there will be flow separation and all that. But right in the what we call the wake of the flow, there is no quote unquote flow separation. Okay. So I would write plume and no flow separation. These are some experiments you can do actually. You take an incense stick and then as the smoke rises, you put maybe your pen over there. Okay, and you will see how the flow, you will be able to see only the flow, how the flow kind of goes around. Okay. I don't recommend heating up your pen and putting it. Okay, but you can at least see what the plume looks like. Okay. All right. Now, for the sphere also, it's a similar situation. Whether it's cylinder or sphere, it's very similar. Okay, sphere also you have a correlation which is different, but overall nature is the same. Okay. Now, this is very interesting for a sphere, for example, where you have this correlation, but the overall, if I draw it similarly, a plume is formed around the sphere. Okay. Now, this is a very practical significance. Or all of us have experienced this, especially now in winter, when the winter is setting in, or maybe December, January in our country. I think all of us have seen that if we go, especially in the evenings, when the outside temperature falls, if you go to a park or an open space, you will see a swarm of mosquitoes on the top of your head. Okay. And wherever you walk, wherever you go, you run, etc., you will see the mosquitoes will come, eventually follow you, and then try to basically gather on the top of your head. So I don't know, you everybody have experienced this? But you guys don't play? Yes or no? Or am I speaking something
Yes,
which?
sir.
Yeah, you have, right? Okay. So what was this? What was the explanation given to you had in your mind so far? Why does the mosquitoes do that? Why do the mosquitoes do that? Okay. Be honest. I mean, how many people thought that it is because they like the black color of your hair? Okay, how many I cannot even figure out here because I'm talking to a screen here. I think that's one of the explanations that is often given. Then some people say, yeah, maybe it's because of your hair oil, etc. But those are not right. Okay, I mean, you ask a bald person, the mosquitoes gather on his head as well, so it has nothing to do with black hair. Okay, you go there without putting hair oil, even then they will come to you. The reason is this: our body temperature, standard at regular healthy individual body temperature is what, between 37 38 degrees C. The outside temperature maybe on a winter evening at a place which gets relatively cold, let's say like Kharagpur, will be about 10 degrees, 12 degrees, 15. So definitely there is a temperature difference of about 20-25 degrees. Correct. So there will be this formation of the boundary layer and the plume on the top of your head, and the mosquitoes actually come and try to position themselves in that plume because they feel the warmth. Okay, that's the reason. Okay, the final thing that I wanted to cover as part of this is flow through vertical channels. Very, very important, because heat sinks. This is what it is. Okay, so let me quickly, sorry, let me end the slideshow. I'll come back to the slideshow again. Ready? Okay. Sorry guys, something wrong. My PowerPoint froze. Okay. Just give me a minute. Task manager. How do I stop the slideshow? Okay, I've stopped my PowerPoint. Let me come here. Okay, so all right, can you see my screen? Probably not, because I have to share. Okay. Chalo. The last topic, 9:38. Very good. We are in good time. Is vertical channels. Okay. So let's say there's a parallel channel. Okay, let's consider two parallel channels or two hot plates forming a channel. Okay. So let us think about this. This length is L. Gravity is acting downwards. So what happens? There's T infinity over here. So there will be a thermal boundary layer, or basically a natural convection boundary layer, which is going to form on this surface. There will be a natural convection boundary layer, which will form on this other surface as well. Okay. So this is piece one. Okay. Widely spaced apart. Okay. So what happens? The boundary layers form independently. So one plate does not feel the existence of the other. Clear? So this is like a vertical flat plate. This is also vertical flat plate. Okay. So each can be treated as a vertical plate vertical flat plate in isolation thermally, okay? Because from thermal point of view, anything that happens outside the boundary layer, you don't care. I mean, it's outside my world. And then I bring them closer. I bring them something like this. Okay, so let me also call this S. So here what happens? My boundary layer forms here. And then my boundary layer on the other plate also forms like this. And then after a certain distance, these interfere. Okay. After distance XL, the boundary layers interfere. So this is like, equivalent of a fully developed flow. Okay. So this happens, and case 3, let me draw it here because I don't have space. It is very close. Then what happens? Sorry. That's it. Very low spacing. So here what happens? Boundary layers interfere or merge right from the start. Right from the start is very close to the start from the beginning. Okay. So one thing please keep in mind, many people say that for, I also said high space, widely spaced, moderate spacing, low spacing, but actually it's all about the length versus spacing. Because if this, for example, if the height of this plate was only, this only till here, then I couldn't have said that this is fully developed and sort of quote unquote fully developed throughout. I could not have done, right? So case 1 is high, high S over L. Case 2, moderate S over L. And case 3 is low S over L. Okay. So now this is what physically happens. So therefore what happens? So average heat transfer coefficient reduces as S over L reduces or L over S increases. Okay. This keep in mind, the average heat transfer coefficient which is average over both walls, will go down if you bring them closer. Fair enough. Okay. Now I need to move back to the slides. What is the simplest way to do that? So here again, there are correlations. Okay. So correlations is again depends on okay. So let's look into this. So there the limits is large spacing and narrow spacing, and actually, as I said more correctly, it is S over L. Okay. So for isothermal plates, this is the correlation. See, the correlation is C1 divided by Rayleigh times S by L. And what is Rayleigh S? Rayleigh S means that the Rayleigh number is defined with the spacing as the characteristic length. So it's G beta delta T S cubed over alpha nu times S over L. So there is first term is something, some constant divided by this term to the power 2. The other one is to the power half. Okay. And this whole thing again is to the power minus 1/2. Okay, this Bar-Cohen and Rosenau has come up with this. Actually, Adrian Bejan, who is pretty much just a genius. Okay, he also came up with this exact form based on his scaling analysis. But the exact correlations are given by Bar-Cohen and Rosenau. Rosenau, we will know more. He's quite pretty much one of the legendary figures of heat transfer. And when we talk about boiling next week, we will know about Rosenau's contributions. Bar-Cohen, Avi Bar-Cohen is also a very, very well-known figure. He just passed away last year and has done a lot of work, especially on electronic cooling, which is also a field that I have worked on for several years now. Okay. If it's an isoflux plates, then also you have similar correlations, except that for isoflux, how do you define Rayleigh number, right? Because Rayleigh number, if it's delta T, you need a temperature. But isoflux, it's not a constant temperature plates. So therefore, the Rayleigh number is replaced by something called Rayleigh star, which is given by this expression on the right. G beta, instead of delta T S cubed, it is Q double prime by K times S to the power 4. Okay, so delta T is replaced by the Q double prime S, which is the isoflux surface flux value, times the spacing over K. You will have it, don't worry, as long as just make sure that you understand what each of these terms mean. You don't have to memorize or anything. Okay. Similarly, the Nusselt number, what you see for isoflux plates, this expression is for the Nusselt number at the top at x equal to L, okay, which is at the top edge. And what is that? Q double prime S, which is the isoflux constant heat flux value, divided by the temperature difference TSL. So which means the temperature at the top, because the temperature is not going to be constant, it is going to be the highest at the top, keep in mind, minus T infinity times S by K. Okay, so again, let me keep it for some time here, and you guys convince yourself that you understand all of these. Now, what is C1, C2? C1 and C2 are constant values, and these values has to be determined from these lookup tables. So Bar-Cohen and Rosenau, I think they did a bunch of experiments to find out these constants. And what they've said is, if it's symmetric isothermal plates, which is both of these plates are at the same temperature, C1 and C2 are 576 and 2.87 respectively. If they're symmetric isoflux plates, same heat flux from both plates, then these are the values. When one is isothermal, the other is adiabatic. And this last one is when both are adiabatic, when they're both insulated plates. Insulated, but at a high, at some temperature. Okay, clear? All right. Okay. So now you see two more terms, which is S max and S opt. Max is for maximum heat transfer, and opt is for, well, one is optimal and the other is maximum. Okay. Now the question is, what is this? All right. Now the maximum heat transfer, that is easy, because as we said, that is the first, when is the heat transfer, what is the spacing at which the average heat transfer coefficient will be maximum, right? When it will be maximum? When when the two boundary layers do not overlap. We saw that as you increase S over L, as you increase the spacing, you will reach a point when the two boundary layers do not overlap. So that's the spacing that is required to maximize the heat transfer. Okay. But then what is optimal, you may ask? Clear. So friends, please listen to this very carefully. Max and opt difference. What is optimal then? Optimal is to maximize the heat transfer. And you will ask, what are you talking about? Okay. What I'm talking about is the following. You have a total width. Let us say your total width that you have, this W, is constant. That is a constraint you have. As a designer, that's the space you have. Now I tell you that you have to design a heat sink or something such that I need to maximize my heat transfer. So what would it be? When you increase the spacing, your average heat transfer coefficient goes up. No question about that. But the number of surfaces for a given W, number of plates that you can accommodate, will also go down. Again, on the other hand, when you bring them closer, what happens is the average heat transfer coefficient goes down, H bar goes down, but the number of plates is more, so that the area is more. And that would give you the optimal spacing. The optimal spacing, as you can see, depends on the Rayleigh number, definitely, or the Rayleigh star, the spacing and the length. And the maximum spacing, definitely, as you can see, is higher than optimal spacing by a factor of 1.71 and 4.77, depending on isothermal or isoflux. So again, to summarize, when they're very, S max corresponds to the spacing when the heat transfer per plate is the maximum. And S opt is when the heat transfer from the whole array of plates is maximum. And that depends on both the average heat transfer coefficient as well as the surface area, which in turn depends on the number of plates you can accommodate over a given width. Clear? This is very important because when we try to design heat sinks for natural convection, we follow this almost blindly, I would say. However, let me also tell you that this is a condition when we are assuming that the flow will go through these plates. I would think of a situation when you're putting a heat sink and then there is ambient air around. The flow will try to bypass the heat sink. Look at the max, think about, imagine the extreme condition when the spacing between the fins is 0. It's like a solid block. Nothing is going to enter, everything is going to go around. Because when the air comes up and sees, oh man, I have to go through this narrow channel, why should I? Let me just go around it. So that's called flow bypass. This analysis, this is for flat parallel channel, so it doesn't consider flow bypass and all. It assumes that this is going to keep on, I mean, this is going to continue infinitely in the lateral direction. but that's not the case. Not infinitely, or basically what I'm saying is, given a total width, it is completely filled with these parallel channels. Okay, so the flow is forced to go through these channels and not around. Okay, that's the limitation of this study, so keep that in mind. Okay, so finally, in the 5 minutes that is left, I'm going to tell you something which is called heat transfer in enclosures. See, all this while, natural convection, all this while we were talking about, hot air will rise and go up, whether it's from a horizontal plate, vertical plate, through channels, around a cylinder, sphere, whatever. But if it's an enclosure, if it's inside a box, and which is what most of our, if you think about the, your desktop tower, or let us say, for example, I have an amplifier of a music amplifier. Many of these electrical cabinets, the inverters, you have seen a lot of these, like battery chargers, etc. These are all have hot components inside. Voltage stabilizer. These all have hot heat generating components inside. Most of them do not dissipate as much heat so that you need a fan or blower inside. And it is cooled by natural convection. Outside electrical cabinets, you have these bus bars carrying electric current. There is Joule heating. Heat is generated. How does it get cooled? So that is where, it's called flow in an enclosure. What happens flow in an enclosure? Let us have a hot plate. This is G. This is TH. This is TC. Okay, unfortunately, I can only use one color on PowerPoint. So what happens? The flow will rise here, definitely. Will get obstructed and then come down like this. And you will have this convection currents set inside the enclosure. Okay, the hot air cannot escape. It will go, get in touch, the air will get heated, turn right angle, come in contact with the cold plate and cool down. And this is how the circulation happens inside. It's like a separate world inside where there is what is called a natural circulation. Okay. So what I've shown here is, this is heated from side. Okay. Maybe I can go to the previous slide. Actually, this is heated from side. I have more space here. Heated from side. There goes natural circulation. This is T hot. This is T cold. It is going to depend on the aspect ratio. If this is still, if you make it very low, then what happens is this 90-degree turn is going to be difficult and you may not have anything. And your convection currents are going to become weaker. And when you come to very, very thin one, this, you will just have what is called a thermally stratified layer from the bottom to top. Okay, so that's heated from the side. And then there are correlations available for Nusselt versus Rayleigh in terms of the spacing between hot and cold plates. So we're not going to get into that. I'm just going to tell you the overall what happens. Now, if you heat it from below, what happens is, for a certain Rayleigh number, which is less than 1708, and this comes from the theory of instabilities. Okay, Rayleigh in terms of height, if it's heated from below and cooled from the top, initially it will just be thermally stratified. Okay, layers of fluid, hot next to the hot plate, then a slightly less hot, less hot, less hot, and finally cold at the top plate. Different layers of fluid with a gradual temperature reduction. So primarily, convection has not set in. Primary heat transfer from the hot to cold is by conduction through air. But then as the Rayleigh number increases beyond 1708, okay, exactly 1708, the convection currents set in. The gravitational forces become strong enough compared to the viscous forces, and therefore the air starts moving in what is called this natural convection loops or cells. Okay, and this is how the flow pattern. The flow rises, gets cooled, comes down. Flow rises, gets cooled, comes down, and this is how things happen. Okay, as you can see, it happens in pairs. From this point, for example, the flow rises, one turns right, one turns left, comes down. Same here. Okay, and this is for Rayleigh number greater than 1708. Here, it's only conduction, this convection. So you have these two-dimensional roles. And then at still higher Rayleigh numbers, these 2D roles change into 3D. Okay, and they appear hexagonal when viewed from the top. By the way, friends, this is also why I'm telling this is called Bénard convection, and these roles or cells is called Bénard cells. Okay, so there's a video here which you can see later, but what you see is this is like boiling of glycerine, and you see some of these cells from the top, these hexagonal cells. This is not impressions on the bottom of the vessel. These are actual cells, Bénard convection cells. And then there's a video where also you can see. Okay, so that kind of brings us to the end of natural convection, and which also brings us to the end of this lecture. So very, very interesting topic, and something that you can visualize, and we see it all around, right? I mean, everywhere around us there's cold ambient and heated plates. Okay, so now that we know what these are, what physically happens, the existence of boundary layers, etc., please try to look around and appreciate what we have learned, both under forced and natural convection. Okay, all right, with that we come to the end of this, and let me stop recording. Tomorrow is a holiday, institute holiday, so please enjoy your Diwali, and next week when we come back we will start with the last phase, which is two-phase flows, condensation and boiling. We cover it in a very elementary manner. These are tough topics, difficult, complex topics, and later on maybe you can take electives on two-phase flows. Okay, I will upload the lecture slides, and I will also upload some practice problems. Okay, so please go through those. The practice problems especially, it will be in the form of a PowerPoint presentation. I'll also upload some convection problem sheet which you can go through. But these practice problems, I would please prioritize and solve them based on the materials that have been covered. And if you can solve those, hopefully you will be in a good condition. Okay, good position to solve other problems as well. All right, thank you very much. See you again on Monday. And as usual, I'm going to stay back for some time to answer any questions that you may have.